Okay, so just to get a straw poll, so how many people have used R before? Okay, so a few. That's good. Maybe half, maybe less than half. And how many people have used mixed effects models in particular? Okay, just a couple. And how many people have used SEM? Okay, also a couple. And then of those who have used mixed effects models, have you used it with R? Okay. Okay, so that might be a bit of review, but I'm also going to, so how I'm going to structure this is I'm going to start with mixed effects models and with longitudinal models in particular, but also covering multi-level models, which are very similar, you'll see. And then, well, actually, after the longitudinal bit, maybe we'll have a bit of coffee break, and then I'll come back and I'll do multi-level, and then I'll discuss some SEM techniques as well. So who went to the Monday talk? Did anyone go to the Monday one? Okay, so I was particularly inspired by Roger's talk, and he has some really great resources online. And so I think we're going to work through those resources that he has in looking at the sort of models that he was proposing for structural equation modeling. So that's a bit about just the structure of how we're going to go through this. So a traditional example that comes up in many textbooks when we're talking about longitudinal data. So this is Pothoff and Roy's dental measurements in boys and girls. So the dental measurement, I think it's the distance between some piece of anatomy and another piece of anatomy in the jaw. I'm not quite sure. But it's looking over 4 time points in both boys and girls. And the great thing about this is it's very balanced. So there's no missing data, which we know is very rare, but it's nice when we're working with that sort of data. And for something like this, you could use a very classical repeated measures analysis, maybe in an ANOVA, but we're kind of going to work through why maybe, yeah, you can come in. Yeah. Thank you. So, if anyone needs an extension cord, there we go. But I'm going to go a bit of why we might use mixed effects models instead. So just some terminology, and I'm taking slides here from Professor Georges Monet. I don't know, Jackie speaks French, but I'm probably butchering that. And he has some really excellent resources that I've used here and that I've put up links to so that you can use as well. So some terminology. So cluster is the set of observations on one participant. So that's the longitudinal element. It can also be something like school or classroom, so anything where there's a sort of cluster of data. And then for the longitudinal data in particular, occasion is the observations at a given time for each subject. Now, when we kind of line all of these subjects up, it's a bit difficult to tell any sort of patterns here when we're looking kind of individually. But when we line them up, we can see maybe some fairly clear distinctions, right? So the slopes are relatively consistent within each sex, or for male and female. But the intercept is really variable, right? So people have different starting points, even though they have the same sort of slope over time. And we're going to be looking at why mixed effects models in particular are really interesting to use for looking at those sorts of questions. So we're going to start why the wrong analysis. And the wrong analysis, and we're all going to know it's very wrong, but one thing that we can do is we can just use linear regression, right? We can just use regression, multiple regression, and we can ignore the fact that there are repeated measures, just chuck all the measures together and kind of do a linear model and see what happens there. And I get the feeling we probably all know that that's the wrong thing to do, but it will help us just kind of work through. And there's just ordinary least squares, the sort of equation that we all know and love very well. So if people can open up their script in R, we're going to get to, what I'm going to do is I'm going to kind of work through it together at the same time, and then we'll do an exercise closer to the end. But if everybody opens up R, this might be what it looks like. And so for those who are just very unfamiliar with R, so on the top left, we have the script. So that's where the sample script should be popping up. And that's where we're going to be highlighting things and running the pieces of code that I've provided there. And then below that we have the console, and that's where the output's going to be coming up. So when we run these scripts, we're going to be getting particular output in there, and we're going to be looking at that output. The variables are up on the top right, and then if we do any plots, they'll be on the bottom right. So do people have like general coding experience, if not in R? Yeah? Okay. So if you have any questions at all at any time, just shout, just let me know. But if we go back, so what we want to do is we want to first just load in the data. So this is the sample data set. So if you highlight these 2 lines of code, and then you press run up at the top, so you see right up there it says run. Is everyone okay with that? Oh, shoot. Yes, of course. I'm so sorry. So first, install the packages, of course. Yeah. So first, we want to, this is the thing that we only need to install them once. So you highlight all of the packages up there and press run, and it'll just work through and install all of those packages. And then every time that you restart R, you'll need to load up the packages. And we'll be doing that as we go along through the script. So everybody okay with downloading the packages? You can't install the packages there.
So we're not doing the whole, all the windows, just the console.
Oh, is it? Okay, so then we are going to have to, are you using RStudio? Oh yeah, okay, so if you just double click on the script, it's going to open it in R, which is kind of the base sort of the language, but then we have RStudio, which has this very nice sort of GUI that we're really interested in using. So what you need to do, sorry, my apologies, is you want to open up RStudio first, and then open up the script through RStudio. So yeah, in the instructions, has anyone else not installed RStudio? Just has R? So I think, okay. So either install it, or if you want to buddy up, that might be good. But everybody else is okay now? Are we having any other problems?
Does it need to take ages to install the packages?
It does take a bit of time.
Okay.
Yeah. It's just going to be running through all of those packages, right? So the packages, I'll just explain a bit about packages, so starting from the bottom up. So R is really great because it's free and it's open source. So the nice thing about packages is that anyone can make one, really. So there are tons and tons and tons of packages, and what's really great about that is that you can have, a particular lab group or a particular person who's interested in some sort of an analysis pipeline that you think that other people might be interested in using. You can code up a package, and then other people can use that package, and that's kind of what makes R really helpful. And so it's kind of modular in this sense, and so that's why I have many of these different packages that we're going to be working through. Some of them are for plotting, some of them are for the SEM, some are for the mixed effects models, and I'll kind of describe the packages that we're using as we go along. But that's kind of one of the things that makes R really good to use in particular. Okay, so have we gotten to the point, can we highlight and run text? No? Not everybody? Who's struggling still? Installing. Okay. Huh. I don't, are you breaking the internet? Yeah, I guess it would be nice if we had like a computer lab. That was our original thought. But the Tinbergen building, the asbestos-laden Tinbergen building kind of ruined those plans. But I thought it would be nice if we did it this way, because then you have it on your computer and like have the script. So maybe in the long term it might be better working out this way. But I can also kind of just get through some of the first bits, and then we can carry on once things have downloaded a bit. So for the first bit is reading in the data. So this is just these 2 lines here are just going to be reading in the data. You highlight it, click run. And first we want to kind of look at the data. right? So the str command, we run that with the data. And what that does is it gives you kind of an overview of what variables that you have. And in particular, what kinds of variables that they are. So you can see, so distance is the dependent measure. So that's the dental measure, whatever it is. And it's numerical. We have age, which is numerical. And then importantly, we have sex down here, which is a factor. So that has 2 levels, male and female. And now, I don't know if you've had this experience in SPSS, but you can also do this in SPSS. It tells you to specify which variables. I've always wondered, does that actually make a difference? I've never been certain, because I put my variables in all sorts of things, and it seems to not make a difference. But when we're using R and when we're using mixed effects models, it is really important to make sure that your variables, if they're categorical, they are coded as factors. And if they're numerical, they are coded as numbers. And so that's why one of the first things I always do is I just call stir on my data and see what it looks like. And then the next call down here is just saying head, and what it does is it gives you just the first couple lines of your data, just so you get a sense of what the data looks like. So again, you have the dependent variable, distance, age, subject, and sex there. Have things downloaded yet, or are we still downloading? Oh no. Wow, I didn't realize it took so long to install. Okay, but I mean, that's fine. We can, the kind of bits where we're doing the worked examples aren't going to be until a bit later, so we can kind of just carry on and then keep going. So first, like I said, we're gonna try the wrong method, right? So we're using just a linear model using multiple regression, and we're gonna see kind of what the output is, even though we know that this is not the best thing to be doing. So for up there, you can see kind of this is the sort of terminology that we use when setting up equations in R. So on the left side, you see distance, so that's the dependent measure. That's what we're trying to predict. You have a little tilde, and that's like essentially the equal sign. And on the right, you have your independent variables. So there we have age and sex. And a bit about, again, the sort of syntax that we're using. I have a little star right there. And so what the star means is it says, give me all main effects and interactions possible. So here, saying age star sex means give me, I want to look at the main effect of age, the main effect of sex, and then the interaction between the two. And so what that would be equivalent to is saying, if you wanted to type it out in the long form, you would say age plus sex plus age colon sex. So this is just kind of a shorthand way of doing it, and that's how I'm going to do it throughout, just because it's a bit easier instead of just typing everything out. And then we're giving it the data over there that we saved it as DD. So there's the data, the dental data there. And we just say summary. So we fit this linear model. This is a multiple regression. And when we look at it, we can see, I don't know why I did that, but we can see then that age is a very significant predictor over there. But the interaction between age and sex is not significant, and neither is there a main effect of sex as well. So this is kind of contrary to what we see, right? So it fails Tukey's interocular test, and again, I'm borrowing some of Professor Monet's slides. And so except for a few irregular male trajectories, on average it looks like that the male slopes are a bit steeper than the female slopes. And this is something that we're not getting because we don't see that interaction when we're looking at just the regular linear model. And you can kind of see this a bit easier when you just look at kind of the overall regression line for each. You can see that it looks like for the boys there is a bit of a steeper slope. And so what this ordinarily squares, what this multiple regression is doing is it's just fitting a one-size-fits-all sort of line to every participant. So it's the same intercept, the same slope for every participant. And when we plot out the participants, we can see that although that might fit pretty well for some people, it definitely doesn't for others. And in particular, what this is doing is you can see this is the covariance variance matrix here, and you can see that the variance is just the same over every time point, and there is no covariance because what it's doing is it's pooling over every time point. It's not even looking at the covariance between multiple time points. And so obviously this is very wrong, right? Because we know that the residuals in the clusters within participants in the longitudinal data are not independent, so they tend to be highly correlated with each other. Okay, so what about repeated measures ANOVA, right? That seems like a natural sort of analysis to be doing here. Why would we use mixed effects models? So in particular, mixed effects models, by using a different method of estimation, so it's using likelihood-based estimation instead of the ordinary least squares. First of all, it gives a less biased estimates of the variance covariance, because what repeated measures ANOVAs do is they assume compound symmetry. So compound symmetry, if we're going back to this variance covariance, it's similar, it's the same variance for each time point. And then if you're looking at the covariance, so the off diagonals, it assumes the same covariance between the time points. And we know that longitudinal data pretty much always doesn't have this structure because points in time that are closer together are going to be more correlated than points that are farther away. So this sort of compound symmetry assumption doesn't really fly with longitudinal data. Another really good thing about mixed effects models is that they allow you to incorporate missing data directly. So there's no need to throw away the incomplete cases. You don't have to delete listwise or impute your values. If you only have two time points for a participant, you can still keep that participant in. But you do have to be very cautious because then your design is going to be imbalanced and there are certain assumptions that might be broken based on that. And then the other good thing is that it allows for including all trials and observations at each time point instead of subject averages. So maybe at each time point you're using some sort of behavioral task, right? And normally you just average over and get, say, accuracy or something, and you get so you do the average and you have one measure at each time point. But what mixed effects models allows you to do is kind of combine, and you can include all trials at each time point and have that sort of cluster structure in the data, which then allows you to incorporate kind of within subject variance as well as between subject variance. And this is also really interesting because what you can do is you can also look at within item variance. And this is something that people talk about a lot in the literature. So if you have, say you have some task and you have the same 20 images or the same 20 words and each participant is seeing the same, you want to make sure that your effect, if you have an effect, is not being driven by one image in particular or one word in particular or one trial. When you use mixed effects models, you can include random effects of the item or of the trial, and you can allow that to be incorporated into the model. How's the downloading now? Are we ready yet? No? Is it going to take a...
Stopped it and it seems to work.
Did yours download all the way or no?
I think it was just some packages or something because I had installed it, but then I just wanted to fix something more.
Okay.
It stopped and now it's open.
Okay. So we can see, so let's see. We could try and do it on a package by package basis and see which ones are the ones that are taking very long, because not everything will need packages.
It was the first one.
It was the first one. What is the first one? I don't remember what the first
The
one
other
is.
ones are they're completely racing through, exactly that.
Okay, and that's the important one. That's the mixed effects model package. Okay, well we can still just keep going through, and then maybe by the end it will be downloaded.
Make sure you're connected to EduRoom and not the cloud, because the cloud was really slow. Basically didn't work at all.
Now I know this for next time. I forgot. I wasn't even thinking about that. Installing the packages obviously requires the internet. I didn't even think about that. Okay, well, for next time. Sorry about that. But I'll just keep going along, and then maybe, hopefully, it'll install at some point. So again, a note about our packages. So there's two main packages that people use when they're using mixed effects models. So one package is the LME4 package, and that's what we're going to be using today, primarily. Although you could also use the NLME package. One reason why I like to use the LME4 package is because it allows for the the glimmer command. I don't know, I always just say it. Some people say GLMER. I say glimmer, it sounds fun. But it allows for the glimmer command, which allows you to use normally distributed data. So you can use gamma distributions for skewed data. You can use Poisson for count data, binomial data. And there's a lot of really interesting things in the literature in particular about binomial data that suggests that if you have that structure, even what people normally do is they'll just take a proportion. So for accuracy, you'll say, oh, this person was 75% accurate. But doing that can violate a lot of the assumptions of the data, and it's much more appropriate to use a binomial distribution with mixed effects models as opposed to just averaging over accuracy data as well. So I put up one paper about that in particular. But the thing about the NLME package is that the good thing about it is that it allows you for specifying specific covariance structures that you might be interested in. So like I was mentioning, autocorrelation in longitudinal data, right? So there's a big problem with autocorrelation in longitudinal data. And what NLME allows you to do is kind of specify these correlation structures. So that's a really good thing that it does. And then also, it can allow you to model heteroscedasticity if you have it in your data, which is much more difficult, if not impossible. I haven't found a way to do it using the LME4 package. So I just wanted to put that note up there just in case people are more interested in kind of working with autocorrelation and heteroscedasticity in particular. So I have the obligatory equations up here. I'm not much of an equation person, so you can just ignore them if you want, which is what I probably would be doing. But just in case people are interested, we're going to ignore the hierarchical one for now. But you see the classic linear model up there that we're all used to. And then on the bottom we have the mixed model for longitudinal data. And there we can see there's two sorts of parts to this equation. So there's the fixed effects. So that's the one with the coefficient of x there. And then there's, or I guess gamma, which one's the coefficient? But and then we have the z portion there, and that's the random effects structure. So it's allowing for not just the residual, not just looking at the error, but also looking at the error within clusters, so within participants, within schools, and that's what makes it the mixed effects, is that you have the fixed effects, but then you also have the random effects where you're looking at error within clusters in particular. So fixed versus random, this was something I got a bit confused about when I was first starting to look at mixed effects models, and there's kind of two ways to look at fixed versus random. And so the first is looking at experimental factors, so things that you're measuring or groups that you're measuring versus a random sample from a population. So for fixed, this is something where you can specify and you're looking at all levels. So it's either social or non-social. You have block 1, 2, or 3, right? Or male or female if you're into that binary. But so it's where you have every single level is described in the data, right? But random is something that you're sampling. So you have a sample of participants. You have a sample of images that you're using. You're obviously not using all of them. So the random effects would then be that thing that you're sampling. And another way of looking at it is looking at observed versus latent variables. So with fixed, those are observed, those are the experimental structure that you're measuring, whereas random, you're looking at latent variables, things like slope and intercept, that you have to extract from the data. So those are just two different ways of looking at it. So if you're interested in more in depth into more of the technical stuff, I would recommend going to Professor Monet's, Jackie, is that right? Monet? How would you say that? Monet, okay. Monet's website, he's got a lot of much more in-depth and technical knowledge. And these are his slides here. I'm just going to go through it very briefly. But like I said, the observations within a cluster are not necessarily independent. And that's why we have this sort of broader conditions when we're looking at the equations. And then the mean response time may depend on time in ways that are far more complex than is typical for other types of predictors when we're talking about longitudinal data. So you might want to be using polynomial models, asymptotic models, splines, and there could be many different partially confounded clocks that you're using. So mixed effects models allows you to kind of go into this deeper sort of structure that's necessary when you're looking at longitudinal data. So a bit about autocorrelation as well. So again, you can look at you can specify different forms of autocorrelation in the data. And again, this is looking at the NLME package, which the script that I've given you isn't really looking at. But just in case for people who are interested, these are various types of autocorrelation structures that you can implement with your data. Okay, is it downloaded at all? Yeah?
Yeah.
Oh, just in time. Okay, so I mean, you can go back and you can do the linear model stuff, but it's not as exciting. So I would just say just skip then to the mixed effects models, which this one is line, is it 24? Yeah? Starting at line 24. So if you highlight these lines, so first of all, we have to load in the package. So this is what you have to do every time. You only have to install it once. But when you open up R Studio for the first time, you have to load in the package. So we say library, LME4. That loads in the mixed effects models package. And then the next line is we're going to specify that model. And then we're going to get the summary output. Is everybody on board? Everybody doing that? Oh, hooray. OK. So first of all, I think my circles got a bit wonky. But I'll just highlight things instead. But so again, we have just the same sort of equation that we were talking about before. This is the same equation that we're using with the linear model. But in particular, this is the new bit that we're looking at. So that's going to be the random. That's a random intercept. So what we're saying here, so we have 1, which is saying the random intercept, bar subject. And we're clustering our data by subject. And what a random intercept is when you're just using a linear model and you're just pooling everything, you're not really looking at the clustered structure, it gets 1 intercept for all of the data, right? But what we're interested in is we're saying we think that the intercept's going to be different based on the subject, which we saw when we were looking at the slopes. And so what this is doing is this is estimating a different intercept, a different mean for every participant. So when we're looking at the summary then, we can see, yeah, this is all a bit off, probably the Mac to PC change. But one thing in particular, so these are the random effects. This is the first bit that we're seeing. And when you look at the variance here, you can see that this is the random intercept that we specified, and it's accounting for, it has more variance than the residual, right? And that suggests that this is something that we should be thinking about and caring about if it does have that much variance. So that's the way to kind of look at the random effects in particular. Ignore my circles. So then when we look at the fixed effects here, the one thing to look at, and this is going to be slightly different on your screen, but is the t-value, right? So you might notice that there are no p-values, right? Has everybody gotten to this summary? Is there anyone who hasn't been able to get the summary?
I think that I don't have all the packages or something.
Oh dear.
I don't know.
Can you buddy up?
Something about matrix, loading required package matrix.
Yeah, that just means it's still loading it. So it might just be taking some time. Yeah, if you buddy up, and then it might come up eventually. But so when we were looking at the fixed effects, and now this isn't aligned nicely anymore, but you can see that there's no p-values, right? And this is something I'll touch on in a bit. But we do have t-values. And Bates, of Pinheiro and Bates, and both of them in particular, they have a nice rule of thumb, and they like to say that if the absolute value of the t-value is greater than 2, it's probably going to be significant. It's probably going to be important, right? So when we're looking at this, we can see that the t-value for age is 10. So that looks like it's probably going to be significant. And then the interaction as well here, we can see that is, again, above 2. So that looks like that might be having an important effect on the model. Okay, so then a nice thing about the mixed effects models is we can look at more than just the random intercept. We can look at random slopes. And so what this is, again, so we've said, okay, we want random intercepts. We want different means for each participant, but we also want the slope to vary per participant. So don't give each participant the same slope. Look at their longitudinal data and specify their slopes. And so for this in particular, we have, this is where we're specifying then the random slope. Is we say 1, which is the random intercept, plus age. And that's our longitudinal variable. So that's where we're going to be wanting to look at the slope. And so again, we can see the random effects. This is so funny. The random effects. And ignore the circles. But we can then, again, look down at the variance. And so, again, we have this random intercept, which seems to have a lot of variance. The slope, not so much, maybe, compared to the residual. And the other important thing to notice here that is the correlation argument. So can everyone see that bit when you're looking at the random? So there's this correlation argument that's saying that, well, actually the intercept and the slope, it looks like they're negatively correlated, right? And that's something just to note, and I'll talk a bit in a bit about why. Okay, back to the fixed effects. The fixed effects look pretty similar, right? Again, if we're looking at the t-values, they look pretty similar there. That's supposed to cover the t-values. And so again, so what this is doing is this is allowing for a different sort of a line for each participant. So you're allowing for a random effect of intercept, so it can start in a different place for each participant, and then also a random effect of slope over time. And so then you can see that it kind of fits much more nicely to the data. Does anyone have any questions at this point? Any other technical problems? Okay. So one question we might be asking is, well, should we include the slope, right? Like I said, it didn't really explain a lot of the variance. There wasn't a lot of variance in slope between participants. So should we even include the random slope? So one way of kind of asking these sorts of questions, and this is something that is really important for mixed effects models, is asking these sort of iterative questions, right? Not just saying, well, this is my model, I'm going to run it, see what happens, but kind of asking yourself, are all the bits and pieces necessary, and kind of getting into the data to see if you need to even specify some of these random effects. And so how we do that is we use a likelihood ratio test with nested models. So nested models means that you have, that one model is nested within the other, right? So you might have a global model, you take out one effect, and then that next model is then nested within the global model. And when you do that, you can call the term ANOVA here. So if you want to call ANOVA on model 1 and model 2 that we've specified, it will give you the likelihood ratio test there, the output there. Yeah? Everybody getting the output? And the thing that you can see is that for the chi-square value and the p-value, it's not significant, right? So what this is doing is saying that there's no really significant difference between these two models. And now when that's the case, one thing that you might want to be looking at next is the AIC value. And I always butcher this. Akeiki's information criterion, I think is what it's called. And the AIC value is just another way of assessing model fit and how good a model it is. And actually for the AIC value, the lower the value, the better the model fit. So we can kind of look at the two and we can say, okay, there's no significant difference between the two, so which one are we going to choose? You can kind of look at the AIC and say, well, model 1 has a lower AIC value, so maybe we'll just stick with model 1. Or you can go with Occam's razor and you can say what's the simplest model and go with the simplest model. But this is this sort of looking at nested models and testing these assumptions about random effects in particular. We use the likelihood ratio test to do that. So correlated intercept and slope. So like I said, there was this high correlation that we saw between the intercept and slope. And it doesn't have to be that way. Like you can also specify the model so that your intercept and your slope are not correlated, right? So correlated intercept and slope means, the higher you are, if it's positive, that means the greater the change. Or if it's negative, the higher you are, the less the change for your starting point. But maybe that doesn't accurately represent your data. And so a way to specify a model without this correlated intercept and slope is up here. So you have just the random intercept here, and then you say 0 plus slope. And that's the notation that you want to use if you don't want to look at a correlated intercept and slope for your random effects. And we can say summary on the second model, and we can see, so now we don't have this correlation term here, because these are two separate things that they're not assessing the correlation. As compared to what we had before, where we had the correlation term there. So again, this is just kind of showing you how, there's not just like one model specification. When you're using random effects, you do kind of want to push the assumptions of, like, do I need to use these random effects, and how do I determine if I need to use these random effects? So again, let's see if there's a difference between correlated and uncorrelated. So we'll do an ANOVA, we'll do a likelihood ratio test, and again, there's no significant difference between the two. And if we look at the AIC values, they're very similar, right? So again, here you might just want to use Occam's razor. You might want to just use the most similar or the most parsimonious model. And actually, in this case, that would be model 2, because having uncorrelated intercepts and slopes is actually using one less parameter. So it is the simpler model in that sense. So then what about repeated measures ANOVA? So let's go back to that, right? That would be a thing that would be really easy to use here. And so what I'm using for here is I'm using the AFEX package, because what I found, and I don't know, people who use R, maybe you can correct me, I found it's actually very difficult to do repeated measures ANOVA in R. And I don't know if that's like a bias, that they really want you to use mixed effects models instead, but I found that it's surprisingly difficult to specify a repeated measures ANOVA. So one of the easiest ways that I found is using the AFEX package and using this call here, easy.glm. And I'm not going to talk too much about the specification, but this is just kind of to show you how you might call the repeated measures ANOVA. And then when you look at the summary, you can see that, again, you have then the significant main effective age, but we have a marginally significant interaction term there, which is suggesting that with using this mixed effects model, we are getting an effect. We are getting an effect that we might not be seeing when we're using the repeated measures ANOVA, and that's probably due to the assumptions between the two. Because a mixed effects model, like I said, so the repeated measures ANOVA uses compound symmetry, but with mixed effects models, it's completely unstructured unless you give it structure. And what that means is that you can have a different variance for each time point, and you can have different covariances, so it's unstructured in that sense. So what about our beloved p-values? So this is a slide from Douglas Bates of Pinheiro and Bates, who wrote the package. So he's pretty much the person to go to. And he talks at length about this. So in some disciplines, there's an expectation that data will be analyzed, starting with the most complex model, and evaluating terms according to their p-values. So this can be appropriate for carefully balanced, designed experiments, but it's rarely a good approach on observational imbalanced data. So bear in mind that this approach was formulated when graphical and computational capabilities were limited. And so he says that a more appropriate modern approach is to explore the data graphically. So again, testing the assumptions and testing like what is really necessary to model this data. And to fit models sequentially, comparing these fitted models with tests such as the likelihood ratio test. So what we've been doing, using the ANOVA term to kind of to use nested models and see what's really necessary for specifying. But I don't know, I'm an experimental psychologist. I think a lot of us might be psychologists. We really want those p-values, right? We want to put them in the paper, and we want to say what's significant. So there's kind of 4 ways that I've experimented with for generating p-values. So the first is, like I said, using this sort of nested approach. And kind of, if you have an interaction term that you're really interested in, you run the model with the interaction term, you run it without, you do the likelihood ratio test, and you see if it makes a difference. And if the model fit is significantly poorer without the interaction term, you can make the argument that that has a significant effect on the model, right? So that's one way of doing it. But sometimes you have very complex models, right? And you want to be asking lots of different questions, and maybe that doesn't make a lot of sense. Another way is using the Kenwood-Roger approximation for degrees of freedom. And we're going to be going over this a bit later, but it's essentially a way of just forcing an F-test out of mixed effects models, which is something that Pinheiro and Bates definitely don't want. But and then the third way is Markov chain Monte Carlo simulations, and this you'll see in some papers, and a lot of papers will use this. I think it's fallen out of favor, and in particular, the creators of the LME4 package strongly warn against using this. And so this is using a simulation approach to kind of bootstrap your data and generate p-values that way. I think of the psychology papers that I've seen, most have used the second approach, so using this Kenward-Rogers approach, and that's something that I'll show you how to do in just a bit. So the fourth approach that I've used is the information theoretic approach using AIC model selection. And so this is used much more frequently in ecology, but ecologists are the ones who've really taken on board mixed effects models and do really complicated and impressive stuff. So I would definitely be trusting them if that's what they do. And what this approach is doing is saying, okay, so instead of doing this sort of, a priori, I'm really interested in this one effect, I'm going to compare both models and see if it makes a difference if I drop out this effect. They kind of use the brute force method, right? So you can put all of your effects in there, all of the fixed effects, all of the random effects, and then what you do is you just do the brute force and you generate every possible model that you can get, right? Using all combinations of the fixed effects. And then what you can do is you can just line them up based on their AIC values and say, which one's the best? And oftentimes people just pick the best model and say, great, this is the best model, so what's in this model must be important, right? The factors that are in there must be important. And that's one approach, but the kind of argument against that is, well, what about the second best model, right? Like, how different is that second best model? And then how if that doesn't have an effect, what argument can we make about including or not including that effect? So the IT approach that's in this book here is they average. They then do model averaging. So you generate every single model, you average it, and then you can get coefficient estimates for each of your fixed effects and confidence intervals because you're doing the averaging. And so you can then say, does this fixed effect, does sex or age, does the estimate for that, is that significantly different than 0? And in which case you can say it has a significant effect on the model. So I can talk a bit more about that later if people are interested in it, because this is the approach that I've been using in particular because it works with particularly complex models. So the Kenward-Rogers approach is pretty effective if you have a few fixed effects, not too many random effects, but if you have very complex models, the models tend not to converge. So the fourth approach is one that I've been exploring most recently, but there's no perfect one-size-all-fits method. It really depends on your data, whether it's observational, experimental, balanced, unbalanced, and those sorts of things. So here's the call then. So again, this is using the AFEX package that we've already loaded in. And the call is then, yeah?
Like, I get a message that I've successfully installed AFEX, but then if I want to add it to the library, I get an error.
Yeah.
That it can't find the function EZGLM.
So even though you've done library AFEX?
Well, there I get the error, actually.
It says online EZGLM was renamed
Oh.
to AOV.
Oh, did they name it recently?
It's now deprecated.
Oh, okay. That shows.
It still works, though.
Does it still work?
No,
It's.
really
No,
Yeah.
Maybe just try reinstalling.
Yeah, but that's what I
Okay.
did getting it.
See, I gave up on trying to do repeated measures ANOVAs in R a long time ago because it was so difficult. So apparently in that time, that call has been deprecated, but.
But I don't need it for all the others.
No. So this is the call. This is a call from the AFEX package, so mixed, and we give it the same equation that we used before when we were calling LMER, lemur, as I call it, limmer and lemur. You give it I don't know if that's what people actually call it, but that's what I call it. And so you run this, and this is going to generate your beloved p-values using the Kenward-Rogers approximation. So here again, we can see that there's a main effect of age, and there is this interaction between age and sex. And that was something that we couldn't see with the multiple regression model. This wasn't something that was as significant when we were using the repeated measures ANOVA. So mixed effects model is kind of giving us that power and allowing us to find this effect. Oh, sorry, question.
So how does power play into this? Because the SEM guru I know is very adamant that I shouldn't include too many paths in my models because when you work with relatively small sample sizes, like 100 or 200, which is kind of small, then creating these very complex models, anyway, in her opinion, means that your model gets quite unstable.
Sure, definitely. And so like when you're using SEM, you have all these rules of thumb, right? So it's like you should have, you need to have more than 5 participants per parameter.
Yeah, that kind of,
Or something. I haven't seen such rules of thumb when you're using mixed effects models, but it's definitely the case that the more complex they are, the less likely they are to run, because you're not going to be able to estimate the variance that you want to be estimating. And for a lot of the time, it will just break, and it'll be obvious that it's not going to work because it won't run. But for that sort of gray area where it does run, but maybe it's not actually giving you a good estimation, you can do these sorts of power calculations using simulation. So there are packages that will allow you to do power calculations with your mixed effects models using simulation. And that's when you can kind of get
Does that impact on which method you use for your model selection? That was what I was wondering. Would you change your model selection method
For
the sample
for
size?
generating p-values, you mean?
Yeah.
I think it might, because if you have, like I said, if you have less complex models, it might just be easier, and it is easier to just run the sort of this mixed call and use the Kenwood-Rogers approximation. If you have more complex models, that's when model averaging might be a bit better to use. But you can't really use model averaging if you don't have enough data, right? So that would be like, I wouldn't always use the model averaging, because if you don't have the ability to estimate those parameters and to do the averages and to have enough of different types of models to be able to do those averages, then that's going to be difficult, yeah.
How does power operate when, in this case, what you're modeling as random effects could be observations as well as subjects? And normally we think of power as subject related, 200 participants.
Certainly.
But actually here you're modeling items, trials. And you may have few subjects, but actually very many trials.
So that depends on the clusters as well. So you have these random effects, and it depends on how many data points are in your clusters, as well as how many then clusters you have. And so that's when using things like more traditional sort of power calculations tend to be difficult, and that's when simulation is much more important. So when you have all these random effects, you can't really get that sort of, do the sort of more traditional power calculations. But when you do the simulations, it does take into account how many observations within a cluster, between clusters, yeah.
In theory, you buy power by having more observations within a cluster.
Yeah. So if you have more time points, longitudinal time points within participants, that's going to allow you to estimate a bit better.
For this example, though, you've got 10 or so in each group.
Yeah.
And 4 observations.
Yeah.
And this is that's sort of a perfectly reasonable number of observations.
Because it's balanced, yes.
Yeah.
If it starts to get unbalanced,
Okay.
then we start to get a bit, you might want to be
but
more cautious.
If it's balanced, then
Yeah.
everything is fine.
Okay, any more questions? Moving on. All my circles that are not in the right spot. Okay, so random effect structure, and this is kind of speaking to some of the things that we've just been talking about. But it is really important to think about your random effects structure. And in particular, there's this one paper that talks at length about it and talks about how we want to keep it maximal, right? So if you have a within subject variable, a repeated measure, so that can be time, that can be if you have 2 conditions within subject, right? You should be estimating that as a slope, right? So you should at least be checking, because the kind of the wisdom is that you want to have the maximal effect structure. So you want to include every single possible slope and intercept that you can from your data, because this paper uses a bunch of simulations to show that so failure to include the maximal random effect structure inflates type 1 errors. And also for designs including within subject or within item, which includes longitudinal data manipulations. If you just use the intercepts and you don't put the slopes in there, it can have catastrophically high type 1 error rates, regardless of how the p-values are calculated. So this is just a note to say that this if you have very complex models where you might have 2 within subject variables and the interaction between the 2 within subject variables, you do have to think very carefully about which slopes you're going to be including, and make sure that you're doing it in the way that's outlined by this paper. Was that confusing? No. Okay. Okay, so checking your data, also something that's very important. So if we highlight this bit of the code here, and we run this, we're going to get a plot, which should look like that. Boom. So it is really, obviously, this is what everybody says, right? Check your data. And here we can kind of see that, well, it looks vaguely normal, except for some outliers here. You can kind of see them here as well. And these are things when you check this, you can kind of see if maybe you want to use a different distribution as well, right? So use the glimmer command to use a different distribution. And you can also check heteroscedasticity, so we can do this by sex. So if you run that code, we get the plots here. And you can kind of see where these outliers are. They happen to be boys in particular. But if you're not looking at those outliers, it looks fairly okay. But I put that in there because I'm sure people are going to want to be checking. Whenever you run a model, you should look at these sorts of things and see how the data look.
Would you use any kind of formal test?
So I don't. I like looking at the data. I mean, there are a lot of formal tests for checking about normality. So there's Kosogrov. I can never say these. Smirnov. Yeah. Those ones. But there are difficulties with both, right? For one, you're supposed to use for big samples. For other, you're supposed to use for small. But for small samples, it's more likely that you're not going to be able to detect if it's non-normal. And for large samples, it's more likely that it's going to say it's not normal, even though it is, right? So I like to look at the data. I mean, it's definitely good to do both and to see what's going on. But I tend to look at the data as opposed to using more formal cutoffs with tests. Do you use tests in particular? Which ones are you interested in using?
I know statisticians would advise to do the visual inspection and decide. I think it's more that if you're hoping,
Yeah.
like keeping the balance of what you see and what you
Yeah. So being objective and subjective. Yeah.
Exactly.
Yeah. Yeah. I think the good thing to do and what people are doing more and what we didn't do in our last paper, which maybe we should have done, is instead of just having things like bar graphs, putting all of the plots and putting like all of the distributions in there. And I think that's something that is to let reviewers and let the people decide if your data is normally distributed and those sorts of things that we don't often do. Yeah. Okay, so I think we should take a break. I think we should have some coffee. Or does anyone have any questions before we have tea or coffee? Yes?
Like, besides the plots, can you get the indices onto this?
Yeah, you definitely can. I don't have that in this script, but I mean, there are whole packages. Again, this is the great thing about R. There are whole packages designed on like testing your data and testing the assumptions of your data and looking at its distributions. So those are definitely, like anything you want, it's in R, I promise, except for repeated measures ANOVAs, apparently. So, yeah.
What about this? How do you know, like if anyone can make a package, how do you know?
Yeah, for sure. So I tend to, that's when you cite things, people cite the packages. And that's really important, is that you can go into the literature and you can see what people are using. I don't think there is any quality control. Is there quality control in R? Sorry?
In order for it to be uploaded on CRAF,
Yeah.
it's quite a bit of quality.
Okay.
Whether it's like statistical
Yeah.
quality
Yeah. Is another. But it has to at least be well documented and that sort of thing. Yeah. Yeah. Okay. That's a good question. But yeah, so whenever I'm using these techniques and putting them in papers, and what people do is they'll cite the packages that they're using. Yeah, so you can do that with structural equation modeling, and that's something we're going to talk about after the break.
in the R program as well.
Yeah, using different packages. Yeah, yeah. So we're going to be looking at a structural equation model package, and we'll be looking at things like latent variables. Yeah. Great. Okay, so multi-level models. So we went over longitudinal models a bit, and multi-level models, to be honest, depending on how many levels you have, is pretty similar, and this isn't going to take too long for us to go over. But the example that I'm using here is, again, from Professor Monet's materials. So this is a high school example. It's from the classic study by Burke and Rodenbush. And the variables that we're using math achievement and socioeconomic status that's measured for students in a bunch of different schools. Some of the schools are public schools. Some of the schools are Catholic schools. So that's the data that we're going to be using. So then if you run these 3 lines of code down here, that's how you'll be able to load in the data. And we're getting this data from GitHub, which is another really cool thing, is that you can, even if something isn't an R package, but somebody has something really fancy on GitHub that you want to use, you can just get different functions off of GitHub or data in particular. Is that okay? Is everybody okay there?
I'm just impressed.
Impressed with R? Yeah, R is very impressive. Yeah. If you get the DevTools package, yeah. So DevTools will allow you to pull stuff from GitHub. Okay, so for this, we have to think then when we're doing multi-level models, we have to think about the levels, obviously. So with this data, it's structured in 2 levels. So we have the students within the schools, and then we also have the level of schools, right? So the sorts of the data that's between schools. So 2 types of variables. So the variables that vary from students to students within schools, we call these level 1. And this is something like SES, sex, individual minority status. So those are the level 1 variables. And then the level 2 variables are the variables that vary between schools and do not vary within schools. So this is going to be sector, whether it's a Catholic or a public school, the mean SES for the entire school, the size of the school, and those sorts of things. Ooh. So again, if we use the head call to get the first 50 lines of data, we can kind of see, and this isn't, I've cut it off, it's not even the first 50 lines here, but you'll see the first 50 lines of data. And we can kind of get a good look at what the data looks like. And again, my circles are going to be off. Yep, totally off. But instead, so for the level 1 variables, so we have SES, sex, minority status, and so you can see that each row is an observation, so each row is a student, and these are the variables that are varying from student to student, so those are the level 1 variables. But then things like sector and things like the size of the school are just kind of repeated over and over again because these are all within the same school. And that's the kind of structure when you want your data in the long format. It looks a bit weird to kind of repeat, the size of the school over and over and over again. But that's how R wants it to be in order for it to understand that that's a level 2 variable, because that variable would then have no variance within the cluster, and that's how it knows that it's a level 2 variable. So again, we can go back to let's try the method that we know is not the best method. So one method is just pooling the data, ignoring the schools, putting them all together, and just doing a regression. And so that's, again, this call up here. We have on the left math achievement, and then on the right side of the equation, we have SES by sector. And that's, again, using the star, so we have the main effects and the interactions there. And we can see we can just do the regression line, and it looks like there is a difference in slope between the public and the Catholic schools there. But we know that this is not a good way of doing it. What's another way that we could do it? So method 2, we could then just take each school separately, and we could fit a regression line for each school, right? Extract these regression lines over here, and then maybe we can then do a step 2 sort of analysis, and we can put those regression lines into an ANOVA or something, or a t-test, and just see if there's a difference in slopes between the two. And you can see that this is slightly better, because when we look at the lines for the fit, when we just do all of them pooled, and then the fit, which is the green, for when we do it based on the school, you can see there are some pretty significant deviations for particular schools. So that's maybe a slightly different, better method. But we want to use multi-level mixed effects models. So this is the call then here for multi-level, and you can see it looks surprisingly similar to what we were doing before. So we have a random effect here. We just have an intercept, a random intercept, clustering based on school. But interestingly here we have SES, which I said is a level 1 variable, so that's varying based on from student to student. And then we have sector, which is a level 2 variable, so varying from school to school. And R can pick that up and knows that the difference between the two. And also, this is, I use these sorts of multi-level, if you call them models, but I don't think of them as such. I think of it more as an individual differences model, because you can look at this, you can do the same sort of thing when you're looking at individual differences from subject to subject. So I would say, I would have a random effect of participant, and then I might have some sort of measure for each participant, maybe average reaction time or something. But then my sort of level 2 variable is going to be something like social anxiety, right? So I have a social anxiety scale, and each person has the same measure. And what you're going to do is that's then also a level 2 variable. And when you put it in the data set, it's just going to have, even though you have all the different trials from one subject, it's going to say the same social anxiety score for every single row. So that's the kind of analyses that I do for looking at individual differences. I don't think of it as multi-level because it still seems like there is just one level to me, but that is an example of multi-level.
Doesn't that apply to like any sort of categorical variable then, like male or female or anything else that you've got?
Yeah.
That's essentially level 2 being categorical.
Yeah.
So you're saying you're putting that into the random but not into the fixed?
Which ones into the random?
Anxiety example that you gave.
No. You would not put that in the random effect structure. No, that's also still a fixed effect, but it's just the way you think about it, right? It doesn't change the analysis. It's just how you think about it, right? And the fact that that variable is going to be just repeated for within each cluster in the data structure. Yeah.
To what extent is it problematic if you have like big difference in, let's say, sample size within schools?
Yeah.
Or like how much your minimal that you need within a school to have it?
So again, I don't know if there's some rules of thumb out there. I think a lot of people determine this sort of thing by simulation and simulating data, but it is going to be a problem if you have a school that only has 5 subjects and then you have a school that has 50, right? That's unbalanced. And so that is something that you definitely need to see how that is affecting, and it's going to be more difficult to estimate using that sort of data.
Sort of related then, so at what point does it become unbalanced? So for
What?
instance, if you've got a single less participant in one school versus another,
Yeah.
is that just treated as
So
unbalanced?
I'm not sure if there are sort of cutoffs or ways that you can diagnose this, right? Because in general, the data that I'm using is trial by trial, and so what's the difference between 80 trials and 60 trials for one? Maybe that doesn't seem so much, but that would be a really interesting thing to look up. Then would be I haven't come across it, how people diagnose this problem of unbalance and when is too unbalanced, but I'm sure there's something out there. Yeah. But we might want to be doing something fancier with nested models, right? And so now our data doesn't have this structure, so you won't be able to run this, but this is just to show you the sort of multiple nesting that you can do. So say you have 3 levels, right? So you have schools, and then you have classrooms within schools, and then you have students. So how you would measure that sort of dependency structure is using the little slash over here. So this is saying that you have schools, and then you have classrooms within schools, and then your level 1 is still the students. So that's pretty much the only sort of difference, the only sort of fancier thing when you're looking at this sort of multi-level models. And there are so many different crazy, complicated ways of specifying these nested models, and this is a pretty good website to try and check out the many different ways that you can specify this. So here, this is one example. This is like a cross and nested design or something. And so you have your level 3, your top level is therapists, and the therapists are seeing several different subjects, and then so that's going to be your level 2, and then the level 1 is actually longitudinal, so you have multiple time points. And so how you specify that, you have this over here. This is a shorthand notation. This is if you write it out entirely. So you can do many different crazy sorts of random, nested random structures. And it kind of boggles my mind a bit. I don't do something as fancy as that, but it's possible. And so this website is a good place to kind of look at several different types of nested structures and how you would implement that using the LME4 package as well as the NMLE package. So big data, right? I haven't even talked about big data yet, really, but this is supposed to be big data with longitudinal and multi-level big data. And I have a lot of friends who are working in big data, and I ask them, like, what is big data? How big of data are we talking, right? And for these friends who are actually big data scientists, they're talking about billions upon billions of data points, right? So when I say, oh, what are the problems? What are things you might talk about in a workshop on big data? It's actually very practical things. It's how do you store this data, right? You store it on the cloud. You can't store it on your computer. And how do you even, have the computational power in order to deal with that data? So I think it's funny, as a humble psychologist, right? For me, big data, I'd be happy having hundreds of participants, right? Thousands of participants. So I think it's funny, the scale of talking about big data. And so when we're using mixed effects models, how might we use these for big data? And there's kind of two types of big data, right? So there's big data in the sense that you have many, many, many subjects, but maybe actually the model that you have is the same sort of model that you'd run with tens or hundreds of subjects, right? So it would be the same sort of thing where you have two variables and the interaction between them and one random effect, right? So that's big in the sense that you have lots and lots of participants, but not necessarily in the kind of the complicated structure of data. And in which case, mixed effects models is really effective. And this is, again, turning to Bates, the expert, and on a course that he teaches. And he does talk a bit about big data. And he gives this example where, again, you have nearly 2 million or something sorts of size of data when you're talking about students in schools in the US. And so that's definitely possible, and it is something that mixed effects models would be helpful for if you don't have so many variables that you're working with. And again, in this case, it's less the analytical strategy and more the practical thing. How do you load this data in R? And the nice thing about R is that it's probably, of all the ways that you could do mixed effects models, it is the most efficient at loading, at computational, at being able to handle the big data that you might have. So there's a lot of different, there's a lot of stuff online about these sorts of questions of the practicalities of big data. And then there's also a lot of papers. So this one in particular is using a Bayesian version of mixed effects models, which is kind of the next step up. And it might seem like a big step, but it's actually not so big. Moving from using Limmer and Glimmer to using MCMCGLM. And so I'm not going to cover that, but just to tell you that it's possible to make that jump relatively easily into using Bayesian models. And that helps with a lot of your sort of convergence problems, right? So people were asking me at the break about convergence problems. I feel ya. Those are big problems, trying to get your models to converge. And actually the solution is to be using Bayesian models. There are a lot of workarounds when you're using mixed effects models, just the normal versions, but the Bayesian ones are really effective at kind of coming up with those sorts of estimation problems. But then there's another sort of big data, right? So not just the number of observations, but the number of variables that you have, right? So maybe you have 20, 30 variables that you're interested in, and you want to look at the relationships between them. So you have a big multivariate sort of data set. And you want to address maybe more causal hypotheses about how these things relate to each other. In which case, structural equation models, SEM, would be the way to do it. And so I'm going to talk a bit about the Lavaan package, which is the easiest way that I found of using SEM in R. It was also, if you were on the talk on Monday, what Roger uses when he does all of his fancy SEM specifications. So just a bit, I'm not going to talk too much about, but like what is structural equation modeling? And I'm not going to talk too much about it because you can look that up a bit later. I want to get into more of the practical bits. But it's essentially looking at, having very, very complex structures, looking at the covariance-variance matrix of these very complicated structures and saying, does the model that you're proposing fit the observed data? And how well does it fit? Using, again, maximum likelihood estimation. So that's just a brief bit about what it's actually doing. Anything more complicated than that, I probably can't help you with. I'm sorry. But so just a bit about notation using the Lavaan package. So it is very similar to when we were using mixed effects models. So when you're doing regression, it's very similar. You have the dependent measure on the left, and then the independent measures on the right. For latent variables, you use the equal tilde sign. And so that allows you to create the latent variable that you've specified on the left. Variance, you use 2 tildes, and you have the same variable. For covariance, 2 tildes, but they're different variables. When you're specifying an intercept, you just say tilde 1, and that's how you specify an intercept. So Lavaan is pretty straightforward, and I think pretty easy to use compared to M+. I found M+ more complicated, I thought, but maybe that's just because I really like R. But if you want to have like more of a step-by-step sort of tutorial of using Lavaan in particular, those resources are definitely out there. They have these sorts of step-by-step tutorials and answer all sorts of questions, including many more types of models than the models that I'm going to be talking about here. So why SEM? So this is a bit about copying a bit of what Roger was saying on Monday, which is that, so say you have 2 time points, and you want to analyze that data, 2 longitudinal time points. One way of doing it is just do a t-test, right? And say, is it different from time point 1 to time point 2? Does it increase? Does it decrease? But that doesn't ask a lot of the questions we might want to be asking. So something slightly fancier is down here. You can use SEM, and you can do these sort of cross-lag path models, which this is something that I've used before in my thesis. And so this is relatively straightforward to do. But again, this is asking, okay, does cog at time point 1 predict neuro at time point 2? Just the value, right? But something that we might be interested in asking is, what about the change? So does where you start with cognition at time point 1 predict the change that you have in neuro, whatever that might be, and vice versa? So those are slightly fancier questions about asking about this change and that sort of longitudinal element that Roger was talking a bit about on Monday. So yeah, so this is, so here, right, so for example, on the top left, we have variance and no mean change. Then we have change but no variance, so it doesn't seem like there is much of a difference between participants, both change and variance. But then on the bottom, you have some really interesting things, right? So you have change and positive covariance. So where you start at time point 1 predicts how much you're going to change. So for positive, the higher you are, the more you change. For negative covariance, the higher you are, the less you change. And you can think about these in the context of depression. So those who are most depressed might be making most changes from some sort of intervention. So these are really interesting questions to ask. So this is the univariate latent change score model. So this is just looking at 2 time points, a measure at 2 time points. And this is something that Roger was discussing, and he was saying that a fancy thing that you can do is you can then, in SEM, you can just specify this latent change score, and you can then ask the question of, does where you start predict this latent change score here? And so I'm going to walk us through, using Roger's materials, how we would specify this in using Lavaan, which maybe is a big leap, but why not? Let's go all in. Okay, so is everybody here at this code? This is what we're going to be looking at here. So I'm going to walk through kind of line by line what's happening. So for the top one, right? So what we're doing there is this is a regression. So we're saying the regression of time 2 on time 1. And what we're doing is we're fixing it to 1, right? So that's why we're doing the 1 star. It means we're fixing the regression coefficient to 1. And what that's doing is that is then, if you look at this equation, right, you have an error term, and that's pushing all of the change onto the error term, right? Because if you're saying cognition at time 2 is equal to cognition at time 1, which is the same as time 2, then it would be plus the change, right? So that's what that first term is doing, is it's kind of pushing the change from time 1 to time 2 into the error, not into the regression term. That's step 1. Is that already too complicated? Or are we with me still? Maybe. Okay. So the next step there is that we're specifying the latent variable of change, right? So we're saying dcog1 is the latent variable of change that we're going to be using. And what we're saying is we're fixing that to time 2. Now, this is getting a bit complicated, but just bear with me for a bit. And then what we do is we constrain the intercept at time 2 to 0, and we constrain the variance at time 2 to 0. Now this all sounds really complicated, and for those of us who might just be very familiar with regression, this makes my head spin a bit, like why are we doing these things? But the short answer is that specifying it in this way, what it's doing is it's creating this latent variable, and it's pushing the change from time 1 to time 2 into that latent variable so that we can then ask these more complicated problems. Because if we didn't create this latent variable, all we would be able to do is say time point 1 predicts time point 2. Not necessarily that where you start at time point 1 predicts change from time 1 to time 2. Are we with me? Okay. So then the next bit is just looking at the intercept, so specifying the intercept for this latent change variable, specifying the intercept for time 1, looking at the variance of the change score itself, so allowing that change score to vary between participant to participant, estimating the variance of time point 1, so again allowing that to vary. And then the final one is the most important one, right? So that's the feedback parameter. That's saying, that's the regression of does time 1, where you start at time 1, predict the change? Okay? So that's this model here, and this is coming from Rogers Materials. So first we want to simulate the data that we're going to be using. So if you run the code, highlighting from library Lavon, all the way through to call means, and run that, that's going to simulate the data for us. And we should get that output there, which is just telling us what the means are at each time point, just for a sanity check. So if we've all gotten that, we're in a good place. And the next part is to run the model. So we specify the model. So everything we say ULCS and everything in between the two quotations. And then we fit it, and we say summary fit. Now some of the important things to look at here. So we have estimator is MLR. So what that is it's a robust estimator. So we use that if we're worried that maybe our data is maybe not normally distributed. We would use the MLR estimator, and that might help account for some of this non-normality. Another sort of thing in this call to the fitting the model that's important is this missing equals FIML. And that's full information maximum likelihood. And so what this is doing is instead of deleting list-wise any missing data, it's using full information maximum likelihood to kind of to fill that in, to allow you to incorporate those participants that might have missing data. Now that sounds really awesome. You're like, oh, sweet. Like I can have missing data with my SEMs. You do have to be very careful because the assumption of this is that you have missing at random or missing at completely at random data, which oftentimes in longitudinal studies is not what we have, right? So you might have that it's the most depressed patients who are dropping out, in which case that wouldn't be random. So we do have to be careful about using that call in particular. So the next thing to notice here is it looks a bit odd, right? So we've got 0, 0, 0. We've got 0 degrees of freedom, right? So what this is a just identified model. So that means that for every parameter we have, we only have one piece of information. So it's overfitting it, right? It's like you do when you have multiple dots and you draw a line that fits through all of the dots, right? It's like the perfect example, which is fine because we'll be able to estimate the model, but we won't be able to make inferences about it because it is a just identified model. It's overfitting. So what we would need in order to kind of make more interesting claims about this data is either to add more data or to do what we were doing previously and do an iterative sort of method of comparing models. And what we'd want to do is we would want to take the same model that we have and constrain one of the parameters, just like dropping out one of the parameters when we were doing mixed effects models, and then do a likelihood ratio test to compare and see if that makes a difference. So what we're going to do here is that's what we're going to do. So the next bit of code is the ULCS2. So we're going to specify the second model. And the important piece there is when I say decog1, 0 star cog T1, that's constraining this self-feedback parameter, so the one that we are really interested in knowing, to 0. And we're going to see if that makes a difference when we compare the two models. So then we do the ANOVA between the two models, and we look, and we see, yeah, there is a significant difference between those models. And when we look at the AIC value, the better model is the first model that doesn't constrain that parameter, which means that dropping out this parameter is making the model significantly poorer. So you can make the argument that that parameter is important and meaningful. And when we look at the graph, I don't know, what do you think is going on here? So I'm saying that where you start does predict how much you change. Does this look positive or negative? Can anyone tell? Does it look like if you start higher, you grow more or grow less? So I would say more too. That's not true. It's actually a negative. But I think it's because it's so dense. You can't really see what's going on. But if you then look at the output from the first model that we fit, so if you go back to all that output that you generated from the first model, and you go and you look at that coefficient term for this self-feedback parameter, so we're saying we want to know if where you start at time 1 predicts change. You can see it's negative, the parameter estimate. So it is actually a negative relationship where the higher you are, the less you change. It doesn't look that way to me, but and again, so going through, this is all wonky, but going through what are the important things to looking at model fit. So the first here is kind of the chi-square test here. And what that is doing is it's comparing the observed data to the model that you've specified and says, is there a difference between the two, right? And actually, if there's a difference, that's bad, right? That means our model isn't really a good fit to the data. So it's kind of counterintuitive, because when the chi-square is significant, that means it's a poor fit to the data. You want it to not be significant. In fact, the higher the p-value, the better, because that means the model that you've specified and the observed data that you have align pretty closely. So that's one way of looking at model fit. And you're not going to get these estimates when it's just identified. This will all just be nonsense. The other thing to look at is the CFI and the TLI. So these are other good indications of model fit. And there we have rules of thumb. So if the CFI is above 0.9, if the TLI is above 0.95, we can make the argument that it's a good fit. But here you can see that these are kind of at odds, the two, right? You want to be looking at multiple indications of fit. And what people do in the literature when they're doing structural equation modeling is they do put all of these indications of fit all together, so you can kind of look for yourself and see if you think that this is a good fit for the model. So now going and looking at the output for the data again, you can see for the intercepts, right? So the intercept at time 1 is the mean, right? This is the mean that we outputted. The intercept for the change, latent change variable, is positive, so we can show that it's increasing from time 1 to time 2. And then for the variance, we see that there is a bit of variance for both the change, so how people are changing, there is this variance, and also where people are starting. So these are sorts of things to look at in the output. Okay, so now we're gonna try something even fancier, and then I'm gonna let you, I'm gonna put a problem up, and kind of let you try and tackle that for a bit, and I'll come around and I'll help. But the other interesting thing is instead of just a univariate latent change score model is a bivariate one, so looking at multiple indicators. And this is coming, again, all from Roger's materials, and there's the link to his open source stuff, and you can download all of his scripts, and he also has this really great sort of tutorial paper that will walk you through a lot of these things as well. And this is what the bivariate latent change score model looks like. So it looks a bit terrifying. But But it's pretty much, it's the same sort of thing with two different measures, and looking at if where you start on neuro, time point 1, predicts change in cog, and the same thing, if where you start in cog predicts change over time in neuro. And here, this is a little sort of app that he has where you can kind of mess around with these parameters and see how it affects your data. So you can mess around with what the intercept should be for cog time 1 and the variance, and have a look and a play and kind of see what these things are doing. But so the question that I'm gonna pose to you then is, okay, so I've given you a full quick tour of Lavon and specifying SEMs in Lavon. So one thing I want to ask is can you specify this model on the left then? So using the regressions and using the covariance in the simple terms that I gave you. So looking at this would be step 1. So this is the more simple model. This isn't the latent change score one. And then also maybe try and specify this more complicated latent change score one. Yeah, good luck. But to get the data in here, you just run the 2 lines of code I said there. So I think that desktop one will work. I'm not positive. That works on mine, but maybe that's different from PCs. And then if you have the data on your desktop, if you have this sample data that I put you in, it'll read in the data. Does that work for everybody? Is everybody getting the data in? So is the file on is the directory wrong? So how do you specify it in PCs? So if you go to your computer, is the default working directory on the desktop? You can, try just loading the data without set the working directory. Does that work? No, it doesn't work? Okay.
Set the directory manually
Yeah.
if you go to session.
Oh, there you go. Because the other thing is if you go to a computer and you just pull out the specific path for your desktop, and then just copy that and put that in where I've put ~/desktop. Does that make sense? If you go to computer and then you click at the directory path and you highlight that entire directory path and just put that in where I've put in between quotes. Yeah. Sure, that works as well.